first. Okay. Okay. So it was my great honor to be here in Caltech to present our research study. I'm very glad that I have a chance to be in here. So today's presentation has been included in the title, which is Exploding Dark Matter Amidst the White Dwarf, with that be an alternative explanation for some peculiar supernovae. During the presentation, I would like you all of you to stay focused and pay attention to a number of keywords listed in the title. For example, dark matter. The fact that most of us have been already familiar with dark matter. But how does dark matter related to a white dwarf? More importantly, how does it being amidst to a white dwarf? And how does exploding such a dark matter amidst the white dwarf provide an alternative explanation to some peculiar supernovae? How peculiar those supernovae are? I assure you that I will answer these questions in the following presentation. I think this is a matter of politeness that I should introduce myself without giving any further presentation. So my name is Leon. I'm a second-year student who is now pursuing for a Master of Philosophy degree in physics in the Chinese University of Hong Kong. My advisors are Professor M.C.G. and Dr. L.M. Lin. During the 2 years of research studies, we collaborate with people outside of our institution. It happened to be Dr. S.E. Leung, who is also a postdoctoral researcher in Canada. Today he is sitting here. So I'm very glad that he recommended me and pursued me to participate in this talk. Without his generous move, I can never be here. I'm really thankful for him. I should start by introducing the motivation to our research studies. I'd like to start by first reviewing dark matter astronomy. Although I bet that most of us have been familiar with dark matter, I would like to still do so as a matter of smooth transition. The study of dark matter dates back at 1970s, where Ralph Rubens et al. Discovers an anomalous galactic rotational velocity curves for this particular galaxy, M31 galaxy. In their study, they plot the rotational velocity curve as a function of distance from the galactic center, and they found an asymptotically flat rotational velocity curve. This is clearly inconsistent with Newtonian prediction, as Newtonian gravity predicts that the rotational velocity should go as 1/r. To resolve this dilemma, astronomer comes up with a non-visible matter model, called the dark matter model, that provides the necessary gravitational force to flatten the rotational velocity curve. In particular, those baryonic normal visible matter that forms the galaxy was being embedded in the background of dark matter halo. However, we are not here today to discuss dark matter halo models. But the key message from the dark matter halo model is that if dark matter and normal matter can form a galactic scale gravitationally bound system, would then it be possible for them to form smaller scale but gravitationally bound system? When I say smaller scale, I mean stellar scale system. Asking this question would lead to the research study of dark matter amidst the stars. To be specific, dark matter amidst the stars ranges from main sequence to complex stars like white dwarf, neutron star, quark star, strange star, or even a solely dark complex star that composites of only dark matter. However, to reduce ambiguity, let us focus on dark matter amidst the complex stars. The studies of dark matter amidst the complex stars date back to 2009, where Sandy et al. Published a visionary research paper named as the effect of mirror dark matter on neutron stars. In their study, they assume dark matter and normal matter as almost separate fluids that form a hybrid star. How do they actually form a hybrid star? I will come back to this point later in the methodology sections. Inspired by their work, Dr. Leung at 2013 studied the effect of dark matter admixture to a white dwarf. In their study, they assume a heavy dark matter particles with mass over 1 GeV, and a degenerate fermionic dark matter with spin 1 half. In this slide, I show one of the representative plots from his paper, where he plot the mass against radius of a series of dark matter mixed white dwarf with an increasing amount of dark matter mixed mass. He found that as we mix more dark matter to the white dwarf, the resulting total mass will be decreasing. Furthermore, in his study, they found that the dark matter fluid component is much smaller in size than that of the normal matter. Inspired by this result, he studied the resulting explosion of a dark matter amidst white dwarfs, namely the dark matter amidst type 1a supernova. I bet that most of us have already heard what is type 1a supernova, but I would like to still recap it. Type 1a supernovas are bright galactic or extragalactic transients that are hypothesized as an explosion of a white dwarf. If the mass of a white dwarf that are about to explode decrease, we expect the supernova are thinner because we have less fuel to burn. But how does it relate to the study of dark matter amidst the white dwarfs? I mentioned that type 1a supernova are bright transients, but not every supernova are that bright. There are supernovae that are very bright, but there are supernovae that are a little bit thinner. They are called the sub-luminous type 1a supernova and has been an ongoing research topic in the field of modeling a supernova. We have just shown that if we mix more dark matter to the white dwarf, the resulting mass will decrease. So it seems that it serves as a very natural explanation to subluminous supernova. Indeed, at 2015, Dr. Lang studied the resulting explosion of a dark matter amidst the white dwarfs. In their study, they assume a large dark matter particle mass over a 1 GeV. Second, in their study, the dark matter component is stationary, it's not movable. This is a very good and appropriate approximation, as we have mentioned that the dark matter component is much smaller in size than that of the normal matter. Third, the total amount of dark matter being mixed is of the order 0.01 solar mass. In this slide, I show one of his representative plots where he plot the volumetric luminosity as a function of time. For these series of dark matter mixed type 1a supernova, having an increasing amount of dark matter mixtures from the topmost line to the bottommost line. They found that if we mix more dark matter to the supernova, the resulting light years are dimmer, which match our expectation. Moreover, these supernova light years seems to serve as a good fit to some observed type 1a supernova that are subluminous, shown as the scatter plot in this diagram. However, it is not the end. Some natural questions to be asked to extend their studies will be the following. First of all, can we mix dark matter particles that are a little bit lighter? Second, could we now take account of the dark matter component motion in the simulations? Third, could we mix more dark matter mass? Asking these questions will lead to our current research studies. Next, I would like to turn to the methodology section. I've mentioned that I will come back to this point later on how dark matter is being mixed to a normal matter. Now is an appropriate time to do so. To be specific, dark matter and normal matter act as an almost independent separate fluids that interact only through gravity. Their interactions through gravity can be reflected in this combined mass term in the momentum equation. Their mass conservation equations, however, are separate. Solving these sets of differential equations could give us global stellar parameters, such as the mass and the radius. For the dark matter, we assume it to be a degenerate fermionic spin 1/2 dark matter. But right now, the particle mass is of 0.1 GeV. The choice for 0.1 GeV, the reason for that is the following. We found that if the dark matter particle mass is very large, for example, this is 10 GeV or 100 GeV, it will be too massive and too compact. It acts as a point gravitational source acting at the center of the grid. Furthermore, we hope that this value, 0.1 GeV, could act as a representative value that generalizes the effect of light dark matter particles. In this slide, I show some examples of dark matter admixed wave drop computed by the dark matter particle mass values that we have chosen. In particular, we have computed 6 models, 6 progenitors of dark matter admixed wave drop with an increasing amount of dark matter admixtures from nearly 0.1 solar mass to 0.5 solar mass. The normal matter central density is fixed into this value, 3 times 10 to the power 9 grams per cc. This is a common choice for white dwarfs that are about to explode. But I should remark that people usually vary is between 1, 3, 5, or 7. But right now, just let us focus on this particular value. We found that as we admix more dark matter to the white dwarf, the corresponding normal matter mass decrease. This could be understood because the normal matter content should reduce itself to accommodate more dark matter lying in the same space. This is also similar to a Chinese metaphor called 2 tigers cannot share one mountain, listed in this cartoon. The tigers at the upper mountain resemble that of the dark matter, and those lying at the lower mountain resemble that of the normal matter. If there are too much tiger in the upper mountain, those at the lower mountain should run away. It seems trivial, but if we sum up the dark matter and normal matter mass to form the total mass, actually the total mass increased at the end. For example, model DM3 has a total mass of 0.115 solar mass, which is greater than the total mass of the pure normal matter model, which is 1.37. Another interesting quantities that we would like to take a look at would be the dark matter radius. We found that if we admix more dark matter to the white dwarf, the dark matter radius increases. This is trivial because now we are pumping more dark matter into the same space. However, we can take a look at the value of the dark matter radius. It is in a similar order to that of the normal matter radius. Take for example, model DM2. It has an almost similar radius for dark matter and normal matter. It could also be reflected in this plot, where I plot the density as a function of distance from the stellar centers for this model DM2 for normal matter and dark matter respectively. Somehow they end up at a nearly similar distance, which shows that they have an almost similar radius. The key message is that now the dark matter has an extended component that is comparable to that of the normal matter. And therefore, the stationary dark matter assumption no longer holds. We need to take account of the motion of the dark matter. These 6 models are very interesting that we would like to explore it to investigate the subsequent supernova explosions. The model explosion, we need a tool, and the tool is a hydrodynamic solver. We adopt a one-dimensional finite volume version of the hydrodynamic solvers computed by Dr. at 2015, where it is a Eulerian grid-based hydrodynamic code with a 5th order reconstruction method. But right now, we need to take account of the fluid motion for both the dark matter and the normal matter that are coupled through gravity. To model the explosion, we need to model the energy source. And to keep track of the energy source, we need to keep track of the individual isotope abundance. because we believe that carbonate supernova are powered by thermonuclear fusions. We adopt a 7 major isotope network, which include helium, carbon, oxygen, neon, magnesium, silicon, and the most important ingredient, nickel-56, where we believe that it is the major power source of the supernova light curves. The simulation duration will be about 5 seconds. This table lists the 6 models that we would like to explore. This model will pop up again and again as a reminder. Next, I would like to turn to the result and discussion sections. First, I'd like to take a look at some global hydrodynamic quantities. For example, the central densities for both the normal matter and dark matter. Central density is a very important indicator that indicates how dense the matter is and how fast the fluids are expanding. In this plot, I show the central density as a function of time plot for these series of dark matter admixed models. We found that as we admix more dark matter to the white dwarf, the resulting normal matter is denser and expanding slower, because now it needs a longer time to reach a lower density value. And this is true also for the dark matter. Another set of important hydrodynamic quantities would be the normal matter temperature, namely the central temperature and the maximum temperature. In this slide, I show the central and maximum temperature as a function of time for these series of dark matter admixed models. We found that as we admix more dark matter to the white dwarf, the resulting normal matter is hotter. So we have shown that if we admix more dark matter to the white dwarf, the resulting normal matter is hotter, denser, and expanding slower. Why would it be the case? It turns out the dark matter gravitational force is strong enough to prohibit the expansion of the normal matter, which could be illustrated in this cartoon. In this cartoon, the pink guy resembles that of the dark matter, and the other guy resembles that of the normal matter. It turns out the dark matter gravity is strong enough to pull back. You want to take a picture? Okay. To pull back the expansion of the normal matter, making it hotter, denser, and expanding slowly. Next, we would like to take a look at the nickel-56 and energy productions. In this slide, in this plot, I show the total energy variation as a function of time for these series of dark matter admixed models. The energy production to be obtained by minusing the asymptotic value of the total energy to that of the initial value, which is indicated at this red arrow. I can do that for these series of dark matter admixed models, and I can obtain the total energy production listed in this table. We found that as we admix more dark matter to the white dwarf, the supernova energy productions are lesser. This could be understood because we have shown that when we admix more dark matter to the white dwarf, the normal matter content is reduced, and therefore now we have less fuel to burn. Next, we would like to take a look at the total nickel-56 mass in solar mass as a function of time for this series of dark matter admixed models. The nickel-56 productions could be obtained by minusing the asymptotic value to that of the initial value listed, which is shown as this red arrow. Again, I do this for all the dark matter admixed models, and I can obtain the nickel-56 mass generated listed in this table. We found that as we admix more dark matter to the white dwarf, the nickel 56 production will be reduced. This is also trivial because we have shown that if we admix more dark matter to the white dwarf, the normal matter content is reduced. So there are less normal matter available to be converted to nickel 56. However, if we take a look at the nickel 56 mass fraction, namely the nickel 56 mass divided by the total normal matter mass, we found that the nickel 56 mass fraction actually increased as we admix more dark matter. Why would it be the case? It turns out hot and dense environment favors the production of nickel 56. We have just shown that if we admix more dark matter to the white dwarf, the normal matters are hotter, denser, and expanding slower. It creates a favorable environment to synthesis nickel 56. And therefore, even now we have less normal matter is available to convert to nickel 56. There are more fractions of the normal matter are being converted to nickel 56. Well, instead of theoretical quantities like temperature, densities, or energy production, we could also compute some supernova observables in order to facilitate observers by comparing observations with theoretical models. Turns out one of the interesting supernova observables would be the supernova neutrinos. As we have heard, supernova neutrinos from a core collapse supernova, a supernova experienced by massive stars, are very strong. But we anticipate it could be detected in, for example, next generation of neutrino detectors. Supernova neutrinos from type 1a supernova, however, are much weaker. However, we anticipate that generation and generation after generation, we could build neutrino detectors that are strong and sensitive enough to capture neutrinos from a type 1a supernova. Indeed, there are already theoretical studies that study the neutrino emissions from a type 1a supernova without any dark matter. It makes sense for us to extend their studies to type 1a supernova having a dark matter admixture. To do that, we need an analytic formula to compute the neutrino emissions from a dense and hot stellar interior environment. To do that, we use an analytic formula package provided by the cococube.asu.edu, maintained by Timus. And this package is actually based on the work by Ito at 1996, where they provide analytic formula in computing neutrino emissions. Well, to be specific, we only consider thermal emission channel of neutrinos, which include pair production, photoneutrino, plasma neutrino, ground stellar, and recombinations. In this slide, in this plot, I show the energy carried away by neutrino as a function of time for these series of dark matter admixed models. The total energy loss carried away by the neutrino could be computed by a simple integral. And I can obtain them and obtain the total energy loss by neutrinos listed in this table. We found that as we admix more dark matter to the white dwarf, there are more energy carried away by neutrinos. This is also consistent with this plot, where, for example, if you take a look at model DM3, it has a much greater area when compared to that of the pure normal matter model. So why would it be the case? Why would there be more thermo-neutrino production if we admix more dark matter? Well, it turns out again, hot and dense environment favors thermo-neutrino production. And we have shown that if we admix more dark matter to the white dwarf, the resulting normal matter are hotter and denser, which create a favorable environment to produce thermo-neutrinos. Somehow, observers are not really interested in the total energy carried away by neutrinos, but they are interested in the total event count registered by a neutrino detector if there were a target supernova happening at a 1 kiloparsec distance, for example, from the Earth. Somehow, there are some under-constructing or proposed neutrino detectors that people have made use of their information to estimate the total event count registered by them, and for a carbon supernova, which is listed in the first column in this table. It is natural for us to extend their studies for dark matter admixed carbonate supernova. To do that, we make use of a simple scaling relations, and we can obtain the event count listed in this table. The key message from this table is that the event count could be notably different from the pure normal matter explosions, only if the dark matter admixture is large, which is indicated at this red circle under model DM1, DM2, and DM3. While neutrino detection would be a future problem, is there anything we can do it right now? Is there anything we can extract from observation to convert observation data from theoretical model right now? It turns out one of the characteristics for a carbonate supernova would be its bright light curve. So it makes sense for us also to compute the supernova light curves. And to do that, we will need to map the density, mass, velocity, and the isotope abundance from our simulation to a package called the SNEC code. The SNEC code is a 1D local thermodynamic equilibrium Lagrangian grid-based radiative transfer code that is capable and good enough to compute supernova light curves. We should also take account of the effect from the dark matter during the light curve modeling phase. And to do that, we will assume that dark matter is a point gravitational source located at the center, exerting a monopole gravity. This is a very good approximation because at the end of the exploding phase, the normal matter usually has a much greater size when compared to that of the dark matter. In this slide, I show the volumetric luminosity against days after the explosion for these series of dark matter admixed modules. We found that if we admix more dark matter to the white dwarf, the resulting supernova light curves are dimmer. This could be understood because we have already shown that if we admix more dark matter, the nickel 56 production could be reduced. Furthermore, normal matter will lose its energy when it will try to expand against the monopole gravity attraction from the dark matter. However, we noticed something very interesting. In this plot, I show some of the observed carbonate supernova light curves. Astronomers have found that observed carbonate supernova light curve exhibit a very interesting relation called the Phillips relation. The Phillips relation tells that if the light curves are brighter, the light curves are broader. And the vice versa is also true. This characteristic makes carbonate supernova a very good distance indicator in cosmic distance measurement. However, we found something that is not so right. We found that if we admix more dark matter to the white dwarf, the resulting explosion has a dimmer light curve. But now the light curves are broader. It is seemingly going against the Phillips relations. Are we breaking any physical laws? Or are we trying to reject empirical findings or observations that has been established for the past 30 years? Certainly not. I would like to remind that even nowadays, the most complex and realistic model with lots of microphysics or multi-dimensional simulation could not reproduce the Phillips relation. That they produce deviation from the Phillips relation, just as what we did. So simply saying that our results are going against the Phillips relation is insufficient to conclude anything. But then, what can be inferred from our results? It turns out that I'm sorry about it. It turns out that one of people will usually analyze light curves in this parameter space, namely the peak magnitude against delta M15 space. Delta M15 measures the decline in brightness 15 days after the explosion the light curve's maximum. And it could be approximated, for example, as half of this error. In this parameter space, we plot the distributions of our dark matter admixed model. And it turns out that the light seems to be lighting on a best fit straight line that goes again in the orthonormal direction of the observed Phillips relation, which is marked at this blue shaded area. As I recap, simply saying that they go in the orthonormal directions to the Phillips relation is insufficient to conclude anything. But we would like to see if there are some observed supernova that share a similar characteristic to our dark matter admixed models. It turns out that there are some peculiar supernova detected by the Palomar transient factor. They are listed as blue squares and green cross. While our dark matter admixed models are listed as red triangles. These peculiar supernova have a characteristic of a little bit thinner peak luminosity, but a very small delta M15, which means they are a little bit thinner, but decline very slowly. Somehow it matches the characteristic of our dark matter admixed models. To be specific, this particular event, called PVF09EIY, even lie closely to our best fit straight line, or even hit the best fit straight line. In short, it seems that our dark matter admixed model could serve as an alternative explanation to these type of peculiar supernova. I mentioned that even nowadays, the most complex realistic multi-dimensional simulation models could not produce the whole Phillips relation, but they produce deviation from the Phillips relations. In the same parameter space, I would like to show how do they deviate. It turns out that people usually vary the model by varying the initial white dwarf composition, which are listed as invert triangles. They could vary the explosion conditions, which are listed as squares. These are observed carbonate supernova that are now believed to be explained by exploding the white dwarf with different mechanisms. As I promised, that they do not reproduce the whole Phillips relation, but they produce a deviation orthonormally from the Phillips relations, just as what we did. Therefore, simply saying that our dark matter admixed models are deviating orthonormally from the Phillips relations is insufficient to conclude anything. However, we can take a look at their position in the parameter space. Either they are having large delta M15, which means they decline very quickly after the maximum of the light curves, or their peak brightness is very large. They could not lie on the parameter space where we could have a supernova that are a little bit thinner, but decline very slowly. Our dark matter admixed model naturally expanded and hit that parameter space. And this parameter space corresponds to the parameter space of some of the peculiar supernova. that are of little bit dimmer, but have a very slow, very small depth M15, which means they decline very slowly. In short, it seems that our dark matter admixed model could help explain certain types of peculiar supernova that are a little bit dimmer, but decline very slowly. I think after about 30 minutes of presentation, it is about time to jump to the conclusion sections. We have done a 1D spherically symmetric simulations of dark matter admixed titanium supernova. In the simulation, the dark matter component is expanded and comparable to that of the normal matter, and therefore the non-movable dark matter assumption no longer holds. And we need to take account of the motion of both the dark matter and the normal matter fluids. We found that if we admix more dark matter to the white shell, the resulting explosion produces a stronger thermo-neutrino signal. These dark matter admixed models could produce dimmer and broader wider light curves that could serve as an alternative explanation to some peculiar supernova that are a little bit dimmer but decline very slowly. At last, I would like to thank all of you spending your precious time in listening to this presentation. So I would like to now turn to the comment and question section. So thank you so much.
Thank you, Leon. Are there questions from the audience here or from those online? Yeah, hi. Thank you. That was a very interesting talk. I guess I have two questions. First, I was wondering if you could say a little bit more about how these stellar scale dark matter halos, I guess, I don't know what they're called, how they're probably properly called, but how do they form? And my second question is if there's a way to get the peak magnitude versus delta M for your models to coincide with some of the other peculiar supernova data points.
So the first question.
Yeah, could you repeat the question before you answer it, just for the microphone?
Okay, so the first question asked is, we show a lot of dark matter admixed stars with an inherent amount of dark matter. So the formation of how those dark matter actually being admixed into a star would be a question mark. This is actually the most of the referee when we would like to publish this paper. Most of the referee asked that. So to be specific, actually, we could not consider dark matter being accreted throughout the age of evolution of the main sequence star, because we have estimated that if we assume a certain amount of dark matter accretion rate, the timing for us to accrete a solar mass scale or near solar mass scale of dark matter would be over the age of universe. Instead, we assume that during the star formation stage, there is an inherent dark matter, ambient dark matter, that are gravitationally bound with the background normal matter in the star forming molecular cloud. And the slight perturbation will make them gravitationally collapse together and form a zero-age main sequence star having a dark matter admixture. We need to give a concrete proof on how this really happened. And to do that, we consider two spherically symmetric constant density distribution of normal matter and dark matter. And the total energy of this fluid is given by this formula. So we can plug in some typical values for the temperature of a molecular cloud, the density for a molecular cloud, the mass of the zero-age main sequence star, and the mass of the dark matter, target dark matter. And solving for E equal to 0, we can get a solution of the initial radii of the ambient dark matter cloud and the density and the required density for the dark matter in this bracket. For example, one of the particular solution would be R1 equal to this value, and the density will be equal to this value. But this seems very large and very crazy, but it's not impossible. For example, there are some state-of-the-art modern simulations of galactic dynamics show that the dark matter density, ambient density near the galactic bulge could be around this value. So it seems that at least we can show that these values are actually possible. But how frequent would a main sequence star born with a dark matter admixture would be another story. So the second question is like, can you after presenting for a slide?
I mean, if there's anyone else that has questions, they can go for.
So is it okay?
Go for it. Okay. Yeah. So the second question is regarding the first slide you showed with the peak magnitude of delta 15. So yeah, and the PTF, yeah, another big kind of group of PTF anomalous supernova, slightly peculiar supernova. I was wondering if your model, which is I think represented by the red triangles, if there's a way that model can be tweaked somehow to explain the other anomalous PTF supernova that are.
So you want to add, okay. So you may let me grab your question. So you like me you would like to ask if some of these dark matter admixed models, for example, this red triangle actually hit on this blue square, isn't it?
Yeah, I mean, or do they have to be in that particular slope and parameter space?
Well, we actually didn't vary the dark matter admixtures until they hit the for example, this particular event 09 EI1.
Okay.
But empirically or qualitatively, we see a trend of going from the upper right direction to the lower left direction. So in theory, if we do a bisection method varies between the dark matter admixture between DM2 and DM3, hopefully they could somehow at the end could hit this particular event. And by very different initial conditions, we have hypothesized that we could generate another set of straight line, for example, in this region. Sorry, in this region or in this region. So they will span a band of dark matter admixed models going from, for example, the lower right direction to the upper left direction. So we have guessed that, but we didn't really take a deep look and do that analysis. I think this is a very good follow-up project. So thank you for your comments about it.
What is the initial condition that you would vary in order to move that line?
Well, the initial condition, there are lots of initial parameters that you could really vary in order to reproduce the physics relations. As I mentioned, we need a different, for example, different composition, different explosion mechanisms, or different initial Voigtlaub mass. So nowadays, even producing a whole physics relation would be a difficult problem. But in theory, if we vary those conditions, hopefully we could really reproduce the physics relation. And for each normal matter model, we can create a set of dark matter admixed models that extend from the physics relation to this lower right corner. And by doing that, hopefully we can span all these parameter space.
Are there other questions?
Can you tell me what kind of equation of state you use for dark matter?
And also the normal matter?
I suspect like normal matter should be like degenerate electron.
Okay.
My turn, sir.
Yeah. Actually, your question, I've also included the slides of appendix that show all the information. So actually, the equation of state for the dark matter is just an ideal degenerate Fermi gas, which could be inferred or referenced from some textbook in compact objects. For example, one of the famous textbook by Shapiro. And as a matter of convenience, I should also introduce the conditions for normal matter. For example, the normal matter equation of state is a finite temperature stellar equation of state called the Helmholtz equation of state. So it includes everything like positron, electrons, ideal gas, or something else. So the temperature for the white dwarf initially is a isothermal sphere of 10 to the power 8 Kelvin. This is the isothermal approximation is very good because we believe that there are lots of free electrons in the white dwarf and they are very good at conducting heat. And the initial composition would be an equal portions of carbon and oxygen. And these sets of initial conditions will be used to solve input into the equation of state in the momentum equation, and we can get masses and radii from the differential equation.
Can I get a small follow-up question? So is the thermal component included, the thermal component included in the equation of state of dark matter as well?
No, there's no thermal component from the dark matter because this is a cold equation of state. We assume it to be a zero temperature equation of state.
Thanks.
Yeah, hi. So I want to ask, so you mentioned that like dark matter, like the admixture of dark matter would violate the Phillips relation. So this could be a potential observational signature, but it's like involved with other factors. Is there any sort of observational like idea for like sort of unambiguously distinguishing dark matter from other methods?
Well, you mean that we have shown that the dark matter admixed model is going in an orthonormal direction from the Phillips relation, and you said that we claim that it is not sufficient. Is
it sufficient or?
No, it is insufficient to conclude anything just by saying that, just by, for example, I erase all the green cross and all the blue square and say that, okay, now I saw an orthonormal direction from the from Phillips relation. So it seems that we found something new. We found that any deviation from the Phillips relation could be explained by the dark matter admixed model. This is a absolute break cross because even nowadays the most of the pure normal matter explosion with a different initial condition with only dark matter admixture also produce deviation from the Phillips relation. But we should highlight that the uniqueness of our model is that they hit a parameter space with a little bit dimmer peak magnitude, but the very small delta M50. These parameter spaces are not achieved by I believe that nowadays up to now by varying the initial pure normal matter explosion model. So this is the most interesting and the selling point of the dark matter admixed model. But of course, we have only compared the observations with theoretical model in a limited parameter space. So a more concrete study would be comparing the whole light curve and with the spectral energy distributions.
Is there a question? I have a question. If you go back to the slide where you show the neutrinos and how they're varying. So what causes the dip here in the neutrino? Like,
You mean this dip?
yeah.
Okay. Actually, we can observe that there are lots of plots that share a similar characteristic. For example, in the neutrino emissions, in the energy generation, and also the necrophysics generation, this is related to the mechanism that we have assumed for exploding this white dwarf. Namely, the deflagration to detonation transition. Well, exploding a white dwarf is somehow similar to exploding something in terrestrial experiment. For example, we would like to explode some firepower. The explosion mechanism can be generalized and separated into two different ways. Now, first of all, is deflagration. Now, deflagration is a subsonic wave that propagates through heat transfer process. For example, turbulence or heat conduction. It releases less energy, and it depends on the microphysics behind the heat conduction. Some of the particular examples for deflagration would be burning something. Detonation, however, is a complete different mechanism. Now, I think most of you has already familiar with this scenario, where in the Middle East there's a explosion of a factory, something like that. But detonation is a propagation of a supersonically shock wave, which is, for example, this cloud. Can you see that? If you really have look at the video of the explosion, you can really see a shock wave propagating outwards. The shock wave compressed material and heat it up, and this heated material provide a positive feedback for this shock wave to make it propagate faster. And therefore, it depends on the hydrodynamics and release more energy from the explosion. The explosion of our white dwarf, I hypothesize, is to be start out as a slow deflagration. Into some particular point, the deflagration becomes a supersonic detonation. And these that I have shown in the neutrino emissions, in the energy generation, the nickel 56, or the central temperature, maximum temperature, or even the density are due to the initiation or are due to the transition to detonations. But I should remark that this is the central density plot. The certain dip here is not consistent with the timing. For example, this is 1.25 seconds. This is not consistent with the timing of the neutrino dip. So which one is corresponding to the which timing is the corresponding timing of the transition is actually this timing. The shock peak in the central maximum, the central density, is due to the fact that during the moment of transition to detonation, there is an inverse converging shock wave propagating back to the center of the white dwarf. And this shock wave and the grid will register this shock wave as an increasing pump in density. Like, for example, some second after the transition to detonation. And that's explain these peaks and why there's a time delay in the peaks for different clocks.
Okay, so the shape really depends a lot on the microphysics.
Hmm?
So if the shape of that neutrino curve depends a lot on the microphysics, then
No.
is it another way that you can test this? Like looking at the timing of the arrival of the neutrinos, or is it then not really observable?
Not really, because this is like some sort of hydrodynamic stuff rather than a microphysics stuff. But I mean the time lag between this peak and the peak register transition event.
Are there any other questions? If not, we're right on the dot at 5, so I think we can end here. So thank you.